Welcome to The Explainer. Today we're tackling something that, well, by its very definition, we shouldn't be able to see it at all. We're talking about an object so incredibly dense, it literally swallows light. Which raises a huge question, right? How on earth did we manage to take a picture of one? And that really is the heart of the problem, isn't it? I mean, think about it. Seeing requires light, but a black hole traps all light. So how do you observe one? It sounds totally impossible. But it turns out, scientists just had to get a little bit creative.
So, the big secret wasn't to look for the darkness itself. Instead, it was to look for the light that's desperately fighting to escape it. The real key was to watch all that superheated stuff and the light rays getting bent all out of shape, right there at the very, very edge of the abyss. I'm talking about the last possible moment before it all just disappears forever. Okay, so before we can even talk about finding a black hole, we really need to get clear on what we're looking for. And let's just, for a second, forget all the crazy sci-fi visuals. In the actual language of physics, what is a black hole? The most important concept here is this boundary called the event horizon. Now, you can kind of think of it as the black hole's surface, not because it's solid, but because once anything crosses that line, the speed you'd need to escape is faster than the speed of light. And since nothing can go that fast, well, nothing gets back out, not even light. And this is probably the most important distinction we need to make. We can never see the event horizon itself. It's totally invisible. What we can see is its shadow. And this dark patch we see in the pictures, it's there because the black hole's gravity is so powerful it actually warps space-time itself, swallowing some light and bending the path of other light all around it. That shadow is what the telescopes are actually capturing. This crazy gravitational warping has a really surprising side effect. The shadow we actually end up seeing is roughly twice as big as the event horizon itself. It's like a cosmic magnifying glass. And this effect, it was a key prediction of Einstein's theories that amazingly astronomers can now actually go out and measure. Right, so if the hole itself is pitch black, where is all that brilliant glowing light coming from in the pictures? Well, the answer is something called the accretion disk. Just imagine this chaotic whirlpool of gas and dust, all spiraling down towards the event horizon. The friction and pressure in that spiral are so intense, they heat the stuff up to millions of degrees. We're talking so hot that it glows brighter than entire galaxies. It's just incredible. Okay, let's bust a really common myth right now. Black holes are not cosmic vacuum cleaners just sucking everything in. Yeah, their gravity is powerful, but really only up close. To put it in perspective, if you swapped out our sun for a black hole with the exact same mass, Earth's orbit wouldn't change one bit. We just keep on circling a dark, cold spot in space. That's it. So, how did scientists actually pull this off? How did they find the evidence? Well, it really required a masterclass in cosmic detective work, using some incredibly clever methods to see the unseeable. The big aha moment, the real breakthrough, was realizing they didn't have to look for the black hole itself. Instead, they could hunt for its dramatic effects on everything around it. On nearby stars and gas, on light, and even on the very fabric of space-time. And these clever workarounds, well, they changed absolutely everything. Okay, the first method was just breathtakingly ambitious. So the Event Horizon Telescope, or EHT, it isn't just one single machine. It's actually a whole network of radio telescopes scattered all across the globe. By synchronizing them with incredible precision, scientists basically created a virtual telescope the size of planet Earth. To give you an idea of its power, that's enough to spot an orange sitting on the surface of the moon. Just wow. And the result? Well, it was one of the most iconic scientific images ever produced. I mean, we've all seen it. In 2019, for the first time ever, humanity saw a direct image of a black hole's shadow, that supermassive giant in galaxy M87. And then, just 3 years later, they did it again, this time capturing the monster at the heart of our very own Milky Way, Sagittarius A star.
All right, the second method is, if you can believe it, even more mind-bending. This one doesn't use light at all. Instead, scientists figured out how to listen. They learned to detect these tiny, faint ripples in the fabric of space-time itself. We call them gravitational waves.
So get this. Einstein predicted these waves all the way back in 1915. But for 100 years, they were just theory. Nobody had ever detected one.
Then, in 2015, the LIGO Observatory picked up this faint little chirp. And what was it? It was the sound of two black holes colliding over 1 billion light years away. In that single moment, a completely new way of observing the universe was born. Just amazing. So, okay, we can finally see them, we can hear them. But what do they actually do? What's the point? Well, it turns out black holes are so much more than just cosmic voids. They are powerful, powerful engines of both creation and destruction. Yeah, we used to think of them as these sort of passive drains in space. But that idea is completely wrong. When a supermassive black hole is actively feeding, it becomes one of the most powerful things in the entire cosmos. It's like a galactic engine that can literally dictate the fate of the billions of stars around it. It works kind of like a cosmic feedback loop. So as the black hole is feeding on that accretion disk, not everything actually falls in. Some of it gets blasted back out in these colossal jets, traveling at nearly the speed of light. These jets then heat up all the surrounding gas in the galaxy, making it way too hot to collapse and form new stars. So in a way, they can actually sterilize their own galaxy. But maybe the most important role black holes play is as these incredible cosmic laboratories. They're these places where our understanding of the universe gets pushed to its absolute breaking point. They literally show us the frontiers of physics. I mean, black holes create conditions that are just impossible to replicate here on Earth. They're the ultimate stress test for our biggest, most fundamental theories, like Einstein's general relativity. And they really point the way toward the physics of the future, precisely by showing us where our current theories completely break down. Deep down, at the very heart of a black hole, lies the biggest mystery of all, the singularity. Now, our current theories say it's a point of infinite density, where all the matter is crushed into zero volume. But here's the thing, whenever you see infinity in physics, it's usually a big red flag that your theory is incomplete. So, is the singularity a real thing? Or is it a sign that we need a whole new theory of quantum gravity to really get what's going on? And then there's this other completely mind-bending idea called Hawking radiation. Basically, when you mix quantum mechanics and gravity right at the event horizon, the math predicts that black holes aren't actually perfectly black. They should slowly leak energy over trillions and trillions of years until they eventually just evaporate into nothing. We haven't proven it yet for sure, but what a profound idea, right? All right, so let's just quickly recap the key takeaways from all this. First, we don't see black holes directly. We see their effects, their shadow, and their gravitational pull. Second, that famous glowing ring you see in the photos, that's not part of the black hole. It's the superheated gas outside the point of no return. And finally, remember that they aren't just passive voids. They are active, powerful engines that can shape entire galaxies. You know, this last thought really captures the whole spirit of black hole science perfectly. The universe hides the object itself, but in doing that, it actually reveals the fundamental physics at play. And through some absolutely incredible ingenuity, we figured out how to see its shadow and listen for its collisions, slowly unlocking its deepest secrets. And that really leaves us with the most exciting thought of all, doesn't it? Black holes are like these giant signposts, pointing us toward a deeper layer of reality that we just don't understand yet. The discoveries so far have been incredible, no doubt. But you get the feeling they're really just the beginning of the story.